Good afternoon. Today I'll be talking about branch and reduce algorithms, in particular how they perform and practice in solving the vertex cover problem. I am going to explain this paper by Takuo Akiba and Yoichi Iwata. Now in theory, branch and reduce is known to have some of the base time complexities for a number of NP-hard problems. Theoreticians have developed very intricate tools to reduce and branch on the problem space to achieve those bounds. However, in practice, the story is different. The fastest practical solvers are usually branch and bound or LP-based branch and cut methods. These rely on strong lower bounds and cutting planes rather than the large sets of reduction rules from theory. The goal of this study was to see if a purely theoretical branch and reduce approach with its many rules can actually be competitive with the best practical solvers in real world and benchmark graphs. Uh, let's start with the problem definition. A vertex cover is a set of vertices in a graph such that every edge has at least one endpoint in the set. The minimum vertex cover problem is to find the smallest such set. This problem is equivalent to the maximum independent set problem. If you take all vertices not in the cover, you get an independent set. In this talk, I will use some graph theory terms like degree, which is the number of edges incident to vertex, and neighborhood, which is a set of vertices adjacent to a given vertex. These will be important in describing the rules of the algorithm. The algorithm we evaluate is a branch and reduce method. It works like this. First branching, we pick a vertex and explore two possibilities: include it in vertex cover or exclude it but include all its neighbors. Reduction, the second step is reduction. Before or after branching, we apply rules that simplify the graph without losing the optimality, for example removing vertices of degree 1. Then packing constraints. This is a new idea introduced here. Extra constraints derived during branching that help prune the search. Lower bounds. Then the next step, before lower bound on the solution size plus we have what we have chosen so far exceeds the best solution bound found. Then we can prune the branch. This combination is aimed at reducing the search space as aggressively as possible. Now, if we want to come to the branching rules, choosing which vertex to branch on is important. The main strategy here is to pick the vertex with the maximum degree. It tends to split the problem more effectively. If there are ties, pick the one whose neighbors have the fewest edges among themselves. In addition, we have mirror branching. If two vertices neighborhoods are nearly identical, we can group them. Then we have satellite branching. If a vertex has a certain neighbor relationship, we can branch in a way that avoids symmetric cases. Finally, the packing branching. This is new in this work. We can decide to exclude a vertex. We add constraints that forbid certain combinations of vertices later in the search, allowing us to prune entire subtrees earlier. Then we come to the reduction rules. The reduction rules simplify the graph while preserving optimality. From theoretical exponential time algorithms, we borrow the degree 1 rule. If a vertex has degree 1, its neighbor must be in the cover. So we include the neighbor and remove both. Then we come to the degree 2 rule, which is the folding. Degree 2 folding. If a vertex has degree 2 and its neighbor aren't adjacent, we can replace the triple with a new vertex, solving a similar graph. Then we have dominance rule. If one vertex closed neighbor contains another, the first must be in the cover. From FPT algorithms, we use the Trotter LP-based reduction, solving an LP relaxation, which always gives variables with values 0, 1 or half, and fixing the zeros and ones. This is computed via bipartite matching. From sparse graph algorithm, we also get confined rule, identify vertices that must be in the cover, twin, funnel and disk. which are used to detect specific subgraph patterns that can be replaced or simplified. Finally, we have packing reduction extend the earlier packing constraints idea of force inclusion or exclusion of vertices when constraints get tight. Now we are coming to the lower bounds. The lower bounds are crucial for pruning. Three ways are used. The click cover bound partition vertices into disjoint clicks. At least click minus one vertices from each must be in the cover. LP relaxation bound from the half integral LP solution. The cycle cover bound explains the partition into cycles and sum the minimal cover size per cycle. The algorithm takes the maximum of these bounds at each step to maximize pruning power. Then we are coming to the parameterized complexity. The study also asks, what if the lower bound is already very close to the optimum? Defining the vertex cover above lower bound problems given a bound b and parameter k. Can we find a cover of size b plus k? Here the two cases were examined, f of click cover bound and f of cycle cover bound. Surprisingly, even when the k is constant, that is the bound is extremely tight, both problems remain parameterized in PR. So even they even very good bounds don't necessarily make the problem easier. Mm, Now for the experimental setup, the experiment compared three solvers, B and R, the branch and reduce implementation with all rules, the Cplex, the commercial branch and cut solver, the MCS, the branch and bound specialized for DIMA CS graphs, tested on large real world sparse graphs like social web and road. The DIMACS benchmark graphs from the old odd cycle transversal reductions. The hardware were basically Xeon X5670 48 GB RAM and each RAM limited to 24 hours. The results were on a real sparse network. The branch and reduce is generally competitive with Cplex and sometimes much faster, especially on larger spatial and large social and wave graphs. In some instances, B and R solved cases where Cplex timed out. On DIMSCS benchmarks, MCS often wins because it's tailored to those instances, but VNDAR still solves many cases competitively. On an odd cycle transversal, branch reduce and Cplex and MCS all significantly outperform the best specified algorithm for the problem. This shows the reducing to vertex cover can always be a powerful approach. Now coming to the conclusion, the few key takeaways were basically branching strategy matters. Maximum degree branching clearly outperforms SATA. The reduction rules matter obviously, and the more the better. The packing-based reduction introduced here gives significant practical benefits. The supposed theoretical algorithms can be very competitive in real-world performance. The challenges the perceptions that theoretical advances only matter for asymptotics. Here, the sophisticated rule sets translate directly to better practice solvers. So, in conclusion, theory and practice can work hand in hand, and the branch and reduce should be considered seriously alongside more traditional practice methods.